Hey everybody, welcome back. Excited for today's lesson. We're going to do volts, amps, and watts. And I'm going to use plumbing as my comparison to start this lesson. So let's start the lesson with the basic operation of your garden hose, because I feel like everybody knows how a garden hose works. You've had a garden hose in your hand with the spritzer on the end that when you shut it off, the pressure's still in the hose, but there's no water flowing, okay? And we're going to use that whole baseline to learn about electricity today is the garden hose and the shutoff valve in your hand when you're using the garden hose, and then the water that flows out of the garden hose, the work that's being done when you squeeze the handle to water the lawn, is the spigot at the end of the hose. When you turn the hose on, the pressure in the hose fills up. So if the valve is closed, all that pressure is sitting in there waiting for you to open it up so the water can flow out through the spigot. Now, in electricity, there's a time variable that comes into play, and we're going to use 1 hour as our time variable today with our water. So if we're hooking up a spigot and we need 1 gallon per hour for that spigot to turn on and run for the whole hour, all right, we're gonna at 24 psi. So all our pressure, the pressure never changes. The pressure always stays the same in your garden hose, right? This section of hose here is going to represent a value of 1 hour, how much water you need for 1 hour to get this variable. So I believe it's like 0.017 gallons a minute have to flow through this pipe, so that if we turn the spigot on for 1 hour into a 1 gallon jug, at the end of the hour, the jug will be full and we will have used all this power in this window, pushing it at 24 psi, right? So we have a pressure, and then we have when we turn the valve on, as soon as we open the valve on the spigot, we get a flow of water, okay? We get a current of water that runs through the hose and comes out the spigot, okay? Now, when we look at this from electrical, it's very similar. So with that said, in electrical, you always have to start with a source voltage or a base voltage. In our homes, we have 220, 240 volts that come in from the power company and feed our house. Now, in our panel boxes in our house, the big stuff in the house, like the clothes dryer, the hot water heater, that all runs off the 220 volt stuff, the higher voltage. It's more pressure, more push on the electric. The smaller things like your toaster, your hair dryer, all that runs off of 110, 120 volts. So it's literally the 240 volt cut in half. So it's half of that pressure. Now in solar systems, you have to determine your supply voltage. It's usually the first step in building your solar system. You have to determine what size voltage and batteries you want to use, and then what components you want to marry up to that. Now 12 volt is used in solar, but being it is such a low pressure, it requires a lot of current. But if you're running most campers are set up for 12 volts, and your car is 12 volts is a good comparison. But very high amps, very low volts. Okay, very high current. 24 and 48 volt are probably definitely the most popular in the solar world. The real big systems, you definitely want to be up here at 48, but there's plenty of people out there building monster systems out at 24 volt. And then there is kind of the redheaded stepchild of the 36 volt, which is a thing, but it's not very common, and there aren't as many parts out, and we ain't doing that today. So The baseline is, when you're starting your solar system, you have to determine what's going to be your supply voltage. What's going to be the pressure in your garden hose system to run the hose or run the wires, right? So we're going with 24 volts today is what the Larry trailer is. But if you're thinking about building a new system, you need to figure out your voltages first so that you're not mix matching parts with things that ain't going to wire up to them. So 24 volt DC, direct current, and direct current means that when the power flows in these batteries, it flows one way. All right, and we'll get to that. So let's go back to our plumbing. Okay, now that we've established voltage. And let's just look at something here real quick with our hose. Okay, so if we have the same pressure on this hose, but we have 2 spigots on the end of it, we need twice the water. So the volume, the current of water in this line has to be double because we're doing double the work. Okay, we need that 2 gallons at the end. And again, it's over an hour time frame. Same concept. Double the spigots, double the load, double the work, double the current. If our pressure stays the same. Now, if we were to double this pressure, we could run 2 spigots off of this much water because with a higher pressure, it's going to push more water. So the math would literally cut this visual in half because it would push it twice as hard. So it would just, it's the way it works. Okay, and then let's move out again and go to 4 spigots at the same pressure pushing the water. Now we need 4 times the current to get to 4 gallons an hour to run those spigots. And once the water runs out, it's gone, it's used up. Okay, it's doing its work. But you can see how the current we need to do that work quadruples from the beginning to the end, to 1 spigot to 4. And again, it's in a certain time frame. Okay? So to stay on our garden hose theory and how our pressure is, or PSI, our push is the pressure in the hose, right? So if we shut this off, and this is at rest, the water's sitting here, but there's no water flowing, okay? And then when you open the valve on the spigot, the water starts flowing and the water starts coming out. Exact same concept with your lights. So you come home and it's nighttime and you turn the lights on, the electrical volts are sitting at the light switch waiting to do work, and when you turn the lights on is the equivalent of hitting the spritzer on the end of the hose, and then the electrons can flow in the electric and it turns your lights on. But the pressure is in there waiting for you to use it at the sink if this was electric. Okay, so let's look at this exact same theory in electrical. Okay, so we've already determined our volts are 24 volts, okay? And just like I had shown you, we're going to use a 1 hour time frame of this electric going through this wire, and the flow is going to be this way to a 1,000 watt inverter. Okay, now for reference only, 1,000 watts is the equivalent to 10 100 watt light bulbs all on at the same time is going to pull 1,000 watts, because each one's 100, you have 10,000 watts. So anytime you hear watt, I want you to think 100 watt light bulb, because that's the work being done in the electrical system. Okay, now in electrical, the math always adds up. All right, and our current in electrical, I'm going to move this. Our current is the amps or the flow of electrical charge through the wire or a solar component. Okay, so exact same concept as the plumbing. You need X amount of power. If I turn this on for 1 hour and it runs, okay, the math says, and we'll get to that, 42 amps is what it's going to be, because we have our supply voltage and we have how much we're going to use, and we just do some division and it gives us 42, and that's our current. That's how many amps we need to run 1,000 watts for 1 hour. And then that's the equivalent of 1,000 watt hours. Okay, and then divided by 1,000 is 1 kilowatt hour. Okay, let's move over here. So now we've doubled the load. We've doubled the sinks. Okay, and electrical, but it's the same concept. We're going to need double the current, double the amps to do the same work, because we've doubled what we put on the end of the wire. Okay, so 24 volts our supply, that never changes. That's our push. That's the pressure in the garden hose. We squeeze the garden hose valve and we turn this on for 1 hour straight. Okay, 1 hour. And this is going to consume 2,000 watt hours. Okay, or 2 kilowatt hours. And obviously the same thing goes. Now, our solar systems are DC. Everybody's heard of AC/DC, right? It's alternating current, it's direct current. So this is a direct current, which basically all it means is, in a battery, the electrons flow to the device is using it, and then there's a flow back. And this has to all be made without interruptions for this to run. Direct current means that in the black wire, and I've taken the black wire and I've cut it open and I've zoomed in on it with a magnifying glass to show you guys what's going on inside. The flow is going this way to our work, right? And like I said, and then returning in the red wire. So we have in direct current, in DC, you have a flow of electric through the black wire to the red wire and back. In your homes, you have what's called alternating current. And basically what that means is the flow kind of really fast, hops back and forth, goes back and forth in this line and back and forth in this line. So it's quite a bit different on how it's feeding, but it's all the same concept. We're not here to talk about AC. Direct current is a straight path through. And then that device works, okay? And then if we go 4 times, you can see we need 168 amps. Now that wire has 4 times the electrons flowing through it in that hour time frame. And that's going to use 4 kilowatt hours. Okay? So that's a real good comparison with the plumbing, and how when you add work, the current of water needs to increase to cover that extra work you're adding onto the end of the hose. And it's the same concept in the electrical. Okay? Okay, so if you want to see what this looks like in real life, let's take a look over here, because I mocked it all up. And here we are. It's the exact same thing. We have our 24 volt battery, our plus and our minus on it. Okay, and then they're wired to the bus bars, and then they go to our 1,000 watt inverter. Okay, now I've done some videos on bus bars, and people don't really understand any of this, don't even know what the hell they are. But basically what the bus bar is, okay, is, if we want to use our water analogy, is basically we're opening up the water pipe and giving us a connection point in that wire. So we're basically opening up the wire and creating a point we can attach into. Now, it acts as a straight wire. So this is literally the drawing I've shown you guys with the straight wires. Now, I did add a shutoff to shut our water pressure off. This is our garden hose knob, our spritzer hose, okay, because we want to be able to if we have to, disconnect from the bus bars. We let go of the spritzer handle on the garden hose, and then that breaks the flow. Then no amps can flow through that. And that would mean it's off, and that wouldn't work. And our pressure would be sitting here waiting to go. And the pressure would still be sitting in that side waiting to go as well. Again, with it disconnected, nothing would be going on in here. But just for a little look of the bus bars, and maybe this is a better view, is just our way of opening up this black wire and this red wire for us to attach more electrical components to it, okay? And give us access to more power to either feed it in or to take it out with the inverter. We feed it in with the charge controllers. All right. And then to understand the flow, because it's DC and direct current, the flow is going to run through here, go through the inverter. The spigot's going to use the water. Okay, the inverter's going to use 1,000 watts if it's running full tilt. And then the electric's going to come back, and we're running it now. So that's on. And anytime you have one of these disconnect knobs, when the knob is in line with the wire, that means it's on. And when the knob is cut across the wire, that means it's off. So we're on and we're flowing. And like I said, if this runs for 1 hour, this will use 1 kilowatt hour. So understand our flow in our DC circuit. And to take this a step farther, if you come out to your solar system and it's dead, this inverter's off and the switch is on, the first thing you'd do is troubleshoot it. You would check your voltage here, check your voltage here, and if there's volts sitting here, if your garden hose is sitting here and it's not spraying when this should be spraying, then that kind of tells you that there's something in there broke the connection. Something in there stopped the flow of the water. So a little quick troubleshooting on top of our lesson here. When you understand the flow of it all, that makes that kind of easy. So just throw that in there quick. So let's get back to this kilowatt hour thing and this unit of measure that we use in electricity. Okay, gallons per hour is the equivalent in the plumbing thing. Okay, we've established our voltage is our pressure pushing. The volts don't change. The pressure doesn't change. The only thing that changes is our flow of electrons, and that's all determined by whatever the device is attached to your circuit. Okay. And again, this is all DC, but let's just zoom back for a little and look at our house, because consumption is a big discussion in the solar world. Okay, you have your house, and the power company runs in 220, 240 AC. All right, and that's what runs into your panel box. Then in the panel box, it can be split to 110, 120. And then let's look at that 1,000 watts, right? Like what in your house running for 1 hour is going to use 1 kilowatt hour? 10 100-watt light bulbs. That's our baseline. So when we think watts, your gas or your oil furnace probably runs around 1,000-watt pull. It's 700, 1,200, depends on what you got. Half horsepower well pump will pull about 1,000 watts. Okay. And these are all 110 appliances. And then 2,000 watts, let's double that. Your coffee pot, your Keurig, your microwave, toaster, dishwasher is probably 20, 2,500. Window AC, 20, 2,500. Could be much lower depending on if you have a high efficiency. And then a 1 horsepower well pump. Now these devices are usually all 120 in your house. Okay, but now we're going to do some real learning on the hogs in your house and what. All right, sorry, I got disconnected there. Like I was saying, our medium loads in our house: dishwasher, AC, 1 horsepower. Now, when we get to the real hogs in the house: clothes dryer, hot water heater, electric range, heat pump, whole house, or a 2 horsepower well pump. These are pulling 4,000 watts. All right, and on a steady pull. Now, when we look at this, if you guys all go get your electric bill and you look at your power company bill, it's all based off of kilowatt hours. And the going rate is about 15 cents a piece. But this is a real good visual on you for something to learn about your electric dryer. So you throw a load of wash in there for 1 hour. And we already know we have our time frame, 1 hour. Your electric washer dryer is 4,000 watts. If it runs for 1 hour, it's going to use 4 kilowatt hours. So if you go to your electric bill and see how many kilowatt hours you're using a month, you know that if you run your dryer for 1 hour, it's going to cost you 4 kilowatt hours, so like 60 cents. But that gives you kind of a picture in your head on how they bill you on your electric bill. It's all based on kilowatt hours. And if you go to your electric bill and you look at it, you probably use between 600 and 1,200 a month is about the going rate. But that's a kilowatt hour. All right. Well, one would be 1,000 watts for 1 hour. But the little stuff doesn't really drink the power. It's these big hog appliances that I mentioned before. These are the ones that are running your electric bill up in your house. That more often than not, this stuff isn't really doing anything. One thing one of the guys did mention to me, being that this is wire, okay, not hose, but we're still carrying electrons through that wire. If we're building a solar system or even wiring our house, right, and these are the loads, okay, you need to make sure that the wire you put in here can usually handle like 50% or double the highest load you got. All right. One of the experienced guys mentioned to me that most of your problems in solar with fires is people undersizing their wires, and then when they get to these real big amp draws, the wire can't handle it. So if I'm wiring my Larry trailer, which is basically wired to run all of these for the most part, I'm 3,500, it's pretty close. All right, for my battery, for this spot down here, you want to use wire to the bus bars that can handle like double that kilowatt, that 4,000 watts. You want it to be able to handle like 8. If you double it now there's more than enough room for the load you're going to be doing in there to travel through the wire and not make any heat. So shout out to Smed. He's over in Sweden. It's freezing. But he brought that one up about making sure, again, if you can, you want to really try to oversize your main wires. And that allows you, when you grow, to be able to clip more of these in, and you don't have to worry because you already have it built into the framework of the system. And that would be these wires here that get you to the bus bars. Okay, that's where you want to really beef that up. Because if I add more loads in here, all right, run another inverter, our volts stay the same and our amps increase, which means our flow in this wire would double if we added another 1,000 watt inverter onto these bus bars. Okay, the volts stay the same, amps double. So to give you a good visual on that. All right, now let's look at what our flow looks like when we have some solar on here. Now, this is what I was saying in some of the earlier videos, like a solar system's job is to take sun, turn it into power, stick it in the battery. Then at night, you use the battery to power your AC, which I just showed you wired up, and make power. So we just looked at the at night usage and flow of electricity when the sun was not up. So now let's look at our flow of electricity during the day. So now our solar's running full blast. We'll say we have 2,000 watts of solar out on the roof. Again, we're back to the watts. But this time, rather than it being work, those watts are coming in to do work and charge the battery, or those amps. And that would be about 85 amps. Okay, so we have our 85 amp charger, right, coming in, and we know our flow is through the black wire, comes in into the battery, and we have a direct path. So then that's taking the sun and pushing it into the battery. So now during the day, our flow is coming in, okay, into the battery. We got to charge that thing up. So to give you a good visual with a solar system, you're both using DC power, using some 24 volts, but then you're producing it, and you have to store it, and you store it in your battery. So there's a good look at the solar side and how that flows. So I feel like I covered everything I wanted to cover. I just went through my notes. Like I said, everybody knows how a garden hose works. And if you think of the current or the flow of the water in a garden hose being the current or the flow of electrons in an electrical wire, or the amps, all right, and then the pressure in that garden hose is your volts, right? And then the higher the pressure, the harder it pushes. To kind of just give you a quick Ohm's law look. Now, since this is 24 volts, if this was 240 volts, like for your house, like we just went over some of the big hot water heater and all that, because of Ohm's law, 240 volts, with this load on the end, all we would do is add a decimal point right in there, 16.8 amps. So that's where that Ohm's law comes into play, where I always say to everybody, the math doesn't add up, like often is my phrase, because my brain is really good at just seeing this and knowing if it's right or if somebody's explaining it to me. But I think I covered everything I wanted to cover. I hope that this video does some good. I feel like I tried to do my best in explaining it and giving a good visual picture in your head of what electricity is and how you can kind of see it compared to water. And it's the same concept. You just can't see electricity. You can't see the electrons flowing through there, all right? So on that note, I would tell you to have an amazing solar day, but it's really nasty out there. Have just an amazing day anyway, and we'll catch you later. Bye-bye.